So here I'd like to talk about what a multiplexer is. Multiplexer short is called a MUX, and these diagrams from Dr. Mealy's text shows the logic circuitry of a MUX. The schematic symbol for this MUX, which is a 4-to-1. The 4 refers to how many inputs. You can see right here there's 4D inputs, and the 1 refers to just the single output. And what's true of all MUXes is that there's a single output and multiple inputs. So you can also have 2-to-1 MUXes, 8-to-1, 16-to-1, and so on. Okay, the bigger number is the number of inputs, and then there's always a single output. So these are the logic diagrams. The schematic diagram for a MUX, a 4-to-1, would look like this, where you have 4 inputs. Typically they're labeled D, but they don't have to be. They can use other variables sometimes. And 1 output, which is typically F. And then you also have select lines. Okay, and for a 4-to-1 MUX you would have 2 select lines. If you have, say, an 8-to-1, okay, 8-to-1 MUX, well then you would have 3 select lines. Okay, because you need 3 possible combinations for a select line to choose from these 8 inputs. And of course a 16-to-1 would have 4 select lines. So if you look at the logic circuitry, first over here to the left, this is the same logic circuitry for a standard decoder. But you can see for a MUX, it's what we had for the standard decoder with additional inputs to the AND gates. Okay, the additional inputs are our data inputs, okay, which are the inputs to the MUX. And then we have an OR gate here that all the AND gate outputs go to, and the output of the OR gate, that's the output of the MUX. So as we saw with the standard decoder, only one of these AND gates will be selected based on what the select inputs are. So for example, when both the select lines are 0, like we said before, because of these inverters, there's 1s at the inputs of at these 2 inputs of the top AND gate, and then at least 1 input of the remaining AND gates is going to be a 0, which is going to make their output 0. Okay, so this is the same discussion we had with the standard decoder in the previous lecture. So if you look at this top AND gate, its output is going to solely depend on D0. That when D0 is a 0, the output will be a 0, and when D0 is a 1, the output will be a 1. So the output of this top AND gate will be equal to the data on input D0. And then, of course, with an OR gate, its output's going to be 1 anytime at least one of the inputs is 1. Since these inputs coming from these bottom AND gates are always 0, well, its output also is going to depend on just what D0 is, and therefore D0 gets passed through to the output. Oops. I'm in trouble with the tablet here, but this would be D0. There we go. And, you know, likewise, if we chose this AND gate with our select lines, D1 would get passed through. Select this AND gate with the select lines, D2 gets passed through. Select this AND gate with our select lines, D3 gets passed through. And that's what this truth table here summarizes. So basically, the way to think about how a MUX works is that it's basically functioning as electronic switch, that the select lines are choosing from the multiple inputs which input gets passed through to the output. So now let's look at some problems involving MUXes from Dr. Mealy's book, And these problems, again, involve some timing diagrams, so we can get some practice with timing diagrams. So you can see here that this is a 4-to-1 mux, and our select line here starts at 0. Okay, this is hex 0 here. So if we just draw a line down like this, okay, during this time, the data on the D0 input gets passed through to the output. So F is just going to equal D0, which is just low the entire time. Okay, then the select line changes right here. Okay, it changes to, that's a 2. So now the data on D2 gets passed through, and it's also low during this time, so F is just going to stay low. Okay, then our select line changes to 1, so the data on D1, which is high, gets passed through to the output F. Okay, then the next select line value we get here is 0. This is 1 here, this is 0. So now the data D0 gets passed through, and you can see that during this time interval that our select line is 0, the D0 data changes, right, from 0 to 1 right there. So at the output, it's going to go 0 right when it gets to that time interval when the select line is 0, and then it follows D0 and becomes high during this portion. So it's the same idea for the rest of this truth table, that just with the select lines, we're choosing which input gets passed through to the output. Okay, here's another example. This is another 4-to-1 mux, and you can see that the select line starts out as 0. And at the time that our select line is 0, the D input is a 1. So this would look like this in binary. And we're selecting the 0th bit. So since the 0th bit is a 1, the F output would be equal to a 1. Now the next thing that changes here is our select line becomes a 1. So now the first bit is going to get selected, and our data is still 1 at this time. So right during this time, now the output's going to go to a 0, right, because it's selecting this bit here. Okay, and then our data changes from 1 to 2 during this time. So now, since the first bit here changed from a 0 to a 1, our output's going to change. So it'll be a 1, and then at this time, our data changes to all zeros. So at this time here, our data is going to go to 0. And now at this time here, oops. Okay, at this time here, our select line goes to 0. So we're going to select bit 0, which is a 0, so it's going to stay 0. Okay, and it would stay 0 up to this point. Okay, and then you should be able to complete this. It's the same idea for the rest of this timing diagram. Okay, here's another example from Dr. Mealy's book. This is another 4-to-1. Now, this is this is input 3 up here. It's kind of hard to see. This is 2, this is 1, this is 0. So we've got our 4 inputs, we got our 2 select lines, our single output attached to D3 input is this data AA, and then to D2 is this data BB, D1 data CC, and D0 data DD. So we're going to start off with a select of 3, so that means the data AA gets passed through to the output. So this is all in hex. So AA is hex 24. Okay, so then now our select line changes. Okay, our select line changes to 1. So that means data CC is going to get passed through to the output. So here the output changes to the CC data of hex 22. And then you can see the CC data changes during this interval when we're selecting D1. So it follows, and at this time right here, it changes to a hex A3. Right here. Yeah, hex A3. Okay, and again, it's the same idea for the rest of this timing diagram. So these timing diagrams, they not only give you practice on how a mux works, but also, again, practice with timing diagrams in this hex notation that we've been talking about. Okay, the last thing I wanted to talk about regarding the mux is that this diagram here shows a common application of a mux. In your Lab 3 design, you're using a mux in a fashion like this. This is a 2-to-1 mux. Okay, we've got 2 inputs in the single output, and since we only are choosing from 2 inputs, well, our select line is just a single bit, because if that single bit is a 0, it's going to allow the data on the D0 input through to the output, and if that select bit is a 1, it will allow the data on the D1 input allowed to the output. So here in this particular diagram, you can see that the muxes are choosing between the output of an RCA and the inputs to the RCA. So this top mux to input 0 is the B input, and to input 1 is the sum output of the RCA. And this bottom mux, it has the sum output to input 0, and it has the A input going to input 1. And then this top mux, the carry out of the RCA is going to determine which one of these 2 outputs gets outputted to F1. If the carry out is equal to 0, F1 is going to equal to B input. If the carry out is equal to a 1, well, F1 is going to equal the sum of the RCA. And down here at the bottom, and this is hard to see here, but this right here is the 0th bit. That's the 0th bit of this sum. So when that 0th bit is equal to a 0, the sum output is going to equal F2, and when that 0th bit of the sum output of the RCA is equal to a 1, well, then the A input gets outputted to F2. So like I said, in the Lab 3 design, you'll be using a 2-to-1 mux to choose from 2 options to get outputted. So it's used in a similar fashion, or the mux that's in your Lab 3 design is used in a similar fashion as these muxes in this example.